Reflecting upon the vast and often silent expanse of the cosmos, we find ourselves relying on incremental, methodical observations to piece together the narrative of our universe. Today, we shall embark on a comprehensive examination of recent astronomical and astrobiological developments. We will analyze the structural anomalies of protoplanetary disks, the revised chronology of Saturn's rings, the biochemical potential of Enceladus, the extreme resilience of microscopic life forms, the advent of autonomous orbital robotics, and finally, a game-theoretic approach to the Fermi paradox. Let us begin by turning our gaze toward the formation of planetary systems. In the vast stellar nurseries of our galaxy, stars are born from the gravitational collapse of molecular clouds. As these clouds collapse, conservation of angular momentum dictates that the material flattens into a rotating disk of gas and dust surrounding the nascent star. These are known as protoplanetary disks. For decades, our understanding of these structures was limited by our viewing angles and the resolution of our instruments. However, a recent discovery has provided a singular case study that challenges our models of disk evolution. We direct our attention to a specific object that has recently garnered significant attention in the astronomical community. It is a protoplanetary disk that has been colloquially named Dracula's Chivito. To understand this nomenclature, one must look to the history of its discovery and the visual analogy it presents. In the annals of astronomy, there exists a well-known object catalogued as IRAS 18059 to 3211, more commonly referred to as Gomez's Hamburger. When viewed through the Hubble Space Telescope, Gomez's Hamburger presents an edge-on view of a protoplanetary disk. The central star is obscured by the thick dust of the disk's plane, the patty of the burger, while the light from the star scatters off the dust above and below the plane, creating two bright lobes that resemble the bun. It is a classic example of a reflection nebula structure where the central engine is hidden, yet its presence is illuminated by the surrounding material. The newly analyzed object, officially designated as IRAS 23077 plus 6707, bears a striking morphological resemblance to Gomez's Hamburger, yet it operates on a scale and with a chaotic internal structure that is distinct. The nickname Chivito is derived from a national dish of Uruguay, a sandwich rich in various ingredients, reflecting the nationality of one of the lead researchers. The Dracula descriptor honors another principal investigator from the Transylvania region of Romania. While the names are whimsical, the physics they describe is profoundly serious. This object, situated at a considerable distance in the northern celestial hemisphere, represents the largest protoplanetary disk known to science at this time. Its sheer angular size allows for a level of detailed dissection that is rare for objects of this class. Observations were conducted using the Hubble Space Telescope, utilizing 6 distinct filters. These filters allow astronomers to isolate specific wavelengths of light, thereby peeling back the layers of the disk to reveal the distribution of different grain sizes and gas temperatures. What the data reveals is a system defined not by the orderly, smooth Keplerian rotation, often depicted in artistic renderings of solar system formation, but by turbulence and asymmetry. In a standard model, a protoplanetary disk should appear relatively uniform as it settles into a stable plane. Gravity and friction act to smooth out irregularities over millions of years. However, the internal structure, The filling of this cosmic sandwich displays a startling degree of chaos. On the northern flank of the disk, extending out to a staggering distance of 3,000 astronomical units, where 1 astronomical unit is the mean distance between the Earth and the Sun, we observe tenuous, elongated filaments. These wisps of gas and dust suggest a system that is not in equilibrium. Contrast this with the southern edge of the disk. Here, the material does not taper off gently into the interstellar medium. Instead, it terminates abruptly, as if sheared by a sharp instrument. This dichotomy between the northern filaments and the southern truncation indicates a dynamic history that we are only beginning to reconstruct. Furthermore, there are anomalous clumps of matter rising significantly above the primary plane of the disk. In a quiescent system, the vertical scale height of the disk is determined by the balance between the vertical component of the central star's gravity, which pulls material down, and the gas pressure, which pushes it up. For massive clumps to exist high above this plane suggests a perturbing force. This could be the result of a dynamic shake-up, a gravitational interaction that has disturbed the system's tranquility. One hypothesis for this disorder is that the disk is still in the process of accreting material from its parent molecular cloud. We may be witnessing the final stages of the star's feeding process, where the remaining envelope of gas is falling onto the disk in a non-uniform manner. Alternatively, the chaos could be driven by gravitational instability within the disk itself. If the disk is sufficiently massive, it can become unstable to its own gravity, leading to the formation of spiral arms and clumps that could eventually collapse into gas giant planets. The absence of astrophysical jets adds another layer of complexity to this analysis. Young stellar objects, particularly Class 0 and Class I protostars, typically exhibit powerful, collimated jets of plasma shooting out from their poles. These jets are driven by magnetic fields and are a mechanism for the star to shed excess angular momentum. The absence of such jets in Dracula's Chivito suggests that the system is relatively evolved. It is not in its earliest infancy. It is an old disk, yet it retains this violent, chaotic structure. This implies that the chaos is not a remnant of birth, but a symptom of current evolution, perhaps the active formation of planets. There is also the possibility of a hidden companion. A massive body, such as a secondary star or a brown dwarf, orbiting within the obscured central region, could be stirring the dust, generating the waves and warps we observe in the outer regions. Binary star systems often disrupt their disks, clearing gaps and launching spiral density waves. Our current observational capabilities face a limitation regarding this object. While Hubble provides exquisite optical and near-infrared imagery, it cannot penetrate the densest regions of the dust lane. To see the bones of the system, the cold, dense gas where the actual accretion is happening, we require sub-millimeter radio astronomy. The Atacama Large Millimeter/Submillimeter Array in Chile is the premier instrument for this task. However, due to the object's location high in the northern sky, it is effectively invisible to ALMA Southern Hemisphere antennas. The Earth itself blocks the view. Consequently, astronomers must wait for the next generation of radio interferometers. The next generation Very Large Array, a proposed network of 250 antennas to be situated across North America, will be required to resolve the kinematics of the gas in Dracula's Chivito. Only then will we be able to map the velocity vectors of the gas and determine if invisible planets are indeed carving paths through this chaotic nursery. until the 2030s, when such facilities may come online. This object remains a tantalizing silhouette of planetary formation physics. We now shift our focus from the birth of planetary systems to the mature architecture of our own solar system, specifically the rings of Saturn. For centuries, these rings have been a subject of fascination, but their physical characteristics, specifically their mass and age, have been notoriously difficult to constrain. The data that has fundamentally shifted our understanding comes from the final phase of the Cassini mission, known as the grand finale. Before Cassini plunged into Saturn's atmosphere in 2017, it executed a series of daring orbits that took it through the narrow gap between the planet's upper atmosphere and the innermost edge of the rings. This trajectory was not merely for dramatic effect, it was a gravitational experiment. By passing inside the rings, the spacecraft could disentangle the gravitational pull of the planet from the gravitational pull of the rings themselves. Previous to this, the two signals were inextricably mixed in the tracking data. By measuring the minute Doppler shifts in the radio signal from Cassini as it was accelerated by the mass of the rings, scientists were able to weigh the ring system with unprecedented precision. The results were surprising. The rings were found to be less massive than many previous models had predicted. In planetary science, mass is often a proxy for age in the context of ring systems. This correlation relies on the concept of pollution. Saturn's rings are composed primarily of water ice, up to 99% pure in some regions. However, the solar system is a dusty place. Micrometeoroids and interplanetary dust constantly rain down upon the giant planets. Over billions of years, this darker, non-icy material should accumulate in the rings, gradually darkening them. If the rings were primordial, that is, if they formed 4.5 billion years ago alongside Saturn itself, they should be heavily polluted and much darker than they appear today. They would be the color of dirty snow. The high purity of the water ice, combined with the lower-than-expected mass determined by Cassini, points to a single, inescapable conclusion. The rings are young. The data suggests an age of perhaps only 100 million years, potentially even less. To put this into a temporal context, when the dinosaurs walked the Earth, Saturn may not have had its iconic rings. They are a recent adornment, likely formed by the tidal disruption of a captured icy moon or a comet that strayed too close to the planet and was torn apart by gravitational forces. This realization forces a paradigm shift in how we view the stability of our solar system. We often perceive the celestial arrangement as static and eternal. However, the youth of Saturn's rings indicates that catastrophic events, moon-shattering collisions and tidal disruptions, are ongoing processes. The rings are transient. Over the next few 100 million years, they will likely decay, raining down into Saturn's atmosphere, leaving the planet as ringless as it was for the majority of its existence. Moving outward from Saturn's rings, we encounter one of its most enigmatic moons, Enceladus. This small, icy world has rapidly ascended the ranks of astrobiological targets. We have known for some time that Enceladus possesses a global subsurface ocean beneath its icy crust, kept liquid by tidal heating, as the moon interacts gravitationally with Saturn. Plumes of water vapor and ice grains erupt from fissures in the South Polar region, famously known as the Tiger Stripes, spraying the ocean's contents directly into space. Recent analyses of the data from these plumes have yielded a critical discovery: the presence of phosphorus. Phosphorus is the limiting element for life as we know it on Earth. It is the P in ATP, the energy currency of the cell, and it constitutes the backbone of DNA and RNA. Carbon, hydrogen, nitrogen, oxygen, and sulfur had already been detected or inferred, but without phosphorus, the biological potential of Enceladus remained chemically constrained. The detection of phosphates in the ice grains indicates that the subsurface ocean is not only rich in dissolved minerals, but possesses a chemistry that is remarkably favorable for life. The concentrations of phosphorus found are estimated to be hundreds or even thousands of times higher than those found in Earth's oceans. This abundance suggests that the interaction between the liquid water and the rocky core of the Moon is highly active. Serpentinization reactions, where water chemically alters rock to release heat and hydrogen, are likely occurring, providing a chemical energy source that could sustain a biosphere independent of sunlight. This discovery has prompted researchers to recalculate the probabilities of finding life on Enceladus. In Bayesian terms, the prior probability of life existing has increased significantly because the environmental constraints have been relaxed. The ocean is not just wet, it is chemically complete. This urgency has revitalized calls for a dedicated mission to Enceladus. Unlike Europa, where the ice shell is exceedingly thick and the ocean is difficult to access, Enceladus offers its samples for free via its plumes. A proposed mission architecture, often referred to as an orbilander, would involve a spacecraft capable of orbiting the Moon to sample the plumes repeatedly, and then landing on the surface to analyze fresh deposits of snow. The primary challenge is bioburden control. We must ensure that we do not contaminate this pristine environment with terrestrial microbes. However, the scientific consensus is shifting. Enceladus may be the most promising location in the solar system to find a second genesis of life. The environment appears to be habitable. The remaining question is whether it is inhabited. Speaking of life and its resilience, let us transition to the field of extremophiles. Our understanding of the durability of life has been expanded by the study of organisms that can survive the harsh radiation and vacuum of space. While the tardigrade, or water bear, is frequently cited as the champion of survival, recent experiments have highlighted other organisms with even more robust capabilities. We turn our attention to the bacterium Deinococcus radiodurans. This organism has been studied for its extraordinary resistance to ionizing radiation. In a high-radiation environment, the DNA of a typical cell is shattered, suffering hundreds of double-strand breaks. For most organisms, this is a lethal event. The genetic instructions are fragmented beyond recovery. Deinococcus radiodurans, however, possesses a unique and highly efficient DNA repair mechanism. New research has illuminated the nuances of this capability. It appears that this bacterium can enter a state that is distinct from the dormancy of a spore. Spore formation, as seen in Bacillus species, involves the creation of a tough, protective shell and the cessation of metabolism. Deinococcus, however, does not form spores. Instead, it enters a suspended state where its biochemistry is optimized for protection. A key factor in its survival is the accumulation of manganese complexes. These manganese ions act as powerful antioxidants, scavenging the reactive oxygen species generated by radiation. By protecting the proteins responsible for DNA repair, the bacterium ensures that once the radiation threat subsides, the repair machinery is intact and ready to reassemble the fragmented genome. This is not merely hibernation. It is a biochemical fortification that allows the organism to effectively resurrect from a state of genomic fragmentation that would be defined as death in any other context. The implications for panspermia, the theory that life can travel between planets, are profound. If biological material can survive the radiation transit between worlds without the need for complex spore formation, the transfer of life may be more common than previously thought. But bacteria are not the only survivors. Experiments conducted on the exterior of the International Space Station have revealed the tenacity of fungi. Specifically, the expose experiment subjected various biological samples to the raw environment of low Earth orbit, ultraviolet radiation, cosmic rays, vacuum, and extreme temperature cycling. Among the samples was a cryptoendolithic fungus, likely a species such as Cryomyces antarcticus or a related black fungus. These organisms are naturally found in the McMurdo dry valleys of Antarctica, living inside the pores of rocks to escape the harsh surface conditions. On the ISS, subjected to conditions that simulate the surface of Mars, these fungi demonstrated remarkable survival rates. After spending nearly a year attached to the outside of the station, a significant percentage of these fungal colonies were able to be revived upon return to Earth. They resumed growth and reproduced. The key to their survival appears to be melanin. This is the same pigment found in human skin, but in these fungi, it is densely packed into the cell walls. Melanin is an excellent absorber of electromagnetic radiation. It dissipates the energy of ultraviolet photons and charged particles, preventing them from damaging the sensitive cellular machinery inside. Some hypotheses even suggest that these radiotrophic fungi can utilize the energy from radiation to drive their metabolism, much like plants use visible light for photosynthesis. Although this remains a subject of active debate, the fact that a eukaryotic organism, more complex than a bacterium, can withstand a year in open space challenges our assumptions about the fragility of complex life. As we contemplate the biological exploration of space, we must also consider the technological means by which we will maintain our presence there. The era of human-only maintenance of orbital infrastructure is slowly yielding to the era of autonomous robotics. Extravehicular activities, or spacewalks, are incredibly dangerous, expensive, and physically taxing for astronauts. A single EVA requires hours of preparation, specifically the pre-breathing of pure oxygen to purge nitrogen from the blood and prevent decompression sickness. The suit itself is a cumbersome spacecraft, and the manual labor fights against the internal pressure of the suit, leading to fatigue and injury. To mitigate this, engineers are developing true robots for space application. These are not merely remote-controlled arms like the Canadarm2, which requires constant human input, but autonomous systems capable of perception and decision-making. Companies and space agencies are testing dexterous robotic systems inside and outside the ISS. One example is the Girai robot, which has demonstrated the ability to perform versatile tasks such as manipulating switches, plugging in cables, and assembling structures. These robots utilize advanced computer vision to identify interface points and force-torque sensors to adjust their grip strength, ensuring they do not damage delicate equipment. The goal is to offload the routine and hazardous maintenance tasks to these machines. The transition is from teleoperation to autonomy. In teleoperation, a human on the ground controls the robot. However, as we move further from Earth to the Moon or Mars, The speed of light time delay renders real-time teleoperation impossible. A signal to Mars can take anywhere from 4 to 24 minutes to arrive. A robot cannot wait 40 minutes for a correction command if it drops a bolt. Therefore, the robot must possess the onboard intelligence to recognize the error and correct it locally. This involves the integration of artificial intelligence for path planning, object recognition, and error recovery. We are witnessing the early stages of in-space assembly and manufacturing. The vision is to launch raw materials and robotic assemblers that can construct large telescopes, solar power stations, and habitats in orbit, bypassing the volume constraints of launch vehicle fairings. The robots currently cutting their teeth on the ISS are the ancestors of the automated construction crews that will build the infrastructure of the future. Finally, we turn to the most profound question in astronomy. Where is everybody? The Fermi paradox posits the contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for, or contact with, such civilizations. A new line of inquiry investigates this through the lens of game theory and the dark forest hypothesis, refined by recent academic papers. The dark forest theory, popularized by science fiction author Liu Cixin, suggests that the universe is a predatory environment. Civilizations remain silent because to broadcast one's existence is to invite destruction by a more advanced, paranoid rival. However, a purely silent universe leads to stagnation. A recent astronomical analysis, often referred to as the asymptotic burnout, or first in, last out hypothesis, attempts to resolve this by introducing the variable of longevity and expansion speed. The argument posits that there is a trade-off between visibility and survival. A civilization that expands rapidly and broadcasts its presence, a loud civilization, consumes resources quickly and makes itself a target. Such civilizations may have short lifespans, burning out or being neutralized. Conversely, quiet civilizations that prioritize concealment and sustainability may survive for billions of years. However, the new research suggests a nuance. It proposes that the dark forest is not a permanent state for all entities. As a civilization matures, its technology eventually reaches a plateau where the cost of hiding outweighs the benefits, or where it becomes sufficiently powerful that it no longer fears aggression. The theory suggests that the entities we are most likely to encounter are those that have exited the forest. These would be the civilizations that have survived the great filters, the evolutionary bottlenecks that destroy most life. They would be incredibly old, likely having transitioned from biological to post-biological or machine intelligence. They would have no need for the resource-intensive expansion that characterizes young civilizations. Their energy consumption would be efficient, perhaps approaching the thermodynamic limits. The paradox is resolved not by assuming everyone is dead, but by assuming that the window of loudness is very short. Humanity is currently in its loud phase, leaking radio waves, sending signals, and searching actively. We are the new children in the forest, shouting to see if anyone answers. The silence we hear is not emptiness. It is the discretion of the survivors. The analysis suggests that if we do make contact, it will not be with a peer civilization of similar age, but with a billion-year-old entity that has chosen to reveal itself, or whose vast, slow infrastructure we finally learn to detect. This implies that our search strategies might be flawed. Instead of looking for radio beacons, which are a sign of youthful inefficiency, we should be looking for technosignatures of vast, stable engineering, stellar shielding, waste heat in the infrared spectrum, or anomalies in planetary system architecture that defy natural formation models. In conclusion, the cosmos reveals itself to be far more dynamic and nuanced than our initial models suggested. From the chaotic, non-equilibrium physics of Dracula's Chivito to the transient, fleeting nature of Saturn's rings, from the chemical readiness of Enceladus's ocean to the biological immortality of Danacoccus, and from the robotic hands we build to the ancient, silent intelligences we seek, the narrative is one of complexity. We are learning that stability is often an illusion, that life is harder to kill than we thought, and that silence in the universe may be a sign of maturity rather than absence. We continue to watch, to measure, and to wait, refining our understanding with every photon we collect.